In this segment, we're going to talk about actually implementing the attention mechanism that we've set up. So recall that our idea here is to have an example like the movie was great and predict a distribution over source sentence positions at each time step in the decoder. And that's going to help us then make better predictions in our output layer. And I guess one thing I'll mention is that we're showing this here for a translation example, but this is very useful in the seek-to-seek semantic parsing and the other sequence-to-sequence problems that we've alluded to. So this is a generally useful attention mechanism that goes way beyond just translation. So what we're going to do is at each time step in the decoder, fundamentally what we want to get is a weighted sum of input states that come out of the input encoder. So I've denoted those here by H1 through H4. And we have at the decoder time step an output H bar 1, which is just the LSTM vector output. And we're going to compare H bar 1 with each of these HI in the input. And that is going to give us a set of scores that we're going to compute using some function. And we're going to refer to these scores as EIJ. So in this case, we have a bunch of scores E1J because we're at the first time step in the decoder, and we are letting J range over all of the positions in the input here. All right. Then what we do is we softmax these. So we exponentiate and normalize them in order to actually turn this into a distribution. Right? So we have like one score per encoder time step per for this particular decoder time step. And so when we exp normalize, we get a distribution over the encoder states. All right, and then we form this vector C by just summing up over J alpha ij times Hj. So we just take a weighted sum of the Hj here, and the weight we use is that probability that we just computed alpha. All right, and then now that we have this C vector, so we have C1 here because it's at the first time step, we are just going to append that with H1 bar and use that to predict our output. And so essentially what we're doing is we are taking this weighted sum of encoder states and feeding that directly into this final matrix multiply and softmax layer in order to inform what the actual prediction and probability distribution over output tokens is going to be. And so we can compare that to what we had before in our standard seek-to-seek model, which simply didn't have this C vector at all. All right, what are the different ways we can do this? So we talked about this function f here. It turns out there's a couple different choices here. One is to concatenate h bar I and hj and multiply them by a matrix and use a tanh function, basically a kind of non-linearity or a kind of one-layer neural network here in order to predict a score. You can also use just the dot product between them or a bilinear product. So basically take the transpose of hi bar, multiply by w, and then multiply by hj. So this is a kind of, you could think of it as a weighted dot product where if you put w in for the identity matrix, you would just recover the dot product. But now we have learnable parameters in here. These w's are trainable parameter matrices that are going to let us learn which tokens we should attend to. And so all of this stuff uses the outputs of the hidden layers as its ingredients. So this is important. It's not using the raw word embeddings, but instead it's doing this after this has all gone through the LSTM. And we'll come back to that point in a second. Okay, but first I want to kind of show some of the alternatives that we can have here. So what we described here is an attention mechanism due to Leung et al. From 2015. But Badenau et al. In 2014 had a slightly different version of this where you basically compute the attention before you feed the input into the RNN cell. So basically the previous RNN hidden state and our current input are used for the attention computation. You feed that into the cell and you get your output, and that RNN cell now is able to consume the results of attention, whereas before the RNN kind of happens all before the attention computation. So it's a little bit, these are different mechanisms. In practice, what people do is they stack up multiple layers of LSTMs anyway, and so exactly what side you put it on doesn't matter as much. But there's kind of multiple ways to do it, and it's an empirical question which one's really better. Okay, so I just want to think a little bit about what exactly attention can let us do. And so here we have a very simple sequence-to-sequence mapping problem, where the problem I've set up is you have a input list of integers, and you want to output the integers that are odd. So an LSTM with attention can very easily learn to do this, and this is not a bad test if you're implementing this, and you just want to test it on some data that you know that the model can deal with. So what happens is that each token here should basically be attending to the corresponding token that it wants to be copying from the input. So first of all, I guess I'll say that if you're attending to a position in the input that's directly above a token that you want to output, it's very easy for the model to learn to just pass that representation through and be able to predict a 3 in the output. So there's no shared parameters between the decoder and the encoder, but this is still something that's pretty easy for the model to learn. All right, and then in terms of actually figuring out how these attentions should be set up, LSTMs can learn to count. So essentially one way to think about what a model could be doing is imagine the LSTM internally has this counter in its hidden state that's just counting up. And then in the decoder, we reset that counter and start from 0. And so the model should prefer to attend to things that are low in the count or at the beginning of the input with a sort of position-based addressing if we assume that there's part of the LSTM hidden state that's doing this. The LSTM can also reject certain inputs, right? So we talked about how, if you're using it as an encoder for sentiment analysis, you can do things like get rid of stop words. And so it can kind of filter out and just not output anything for 0 and 2, or, it has to output something, let's say, but, it outputs vectors that are not going to be picked up by the decoder. And so in combination, these individual skills, again, we can't actually point to units in the LSTM easily and say that this is what they're doing, but this intuition you should have should allow you to justify to yourself, okay, here's why it can learn to do this, because I know it has this capability and I know it has this capability, and maybe it's just sort of combining those things. You can come up with these stories for kind of justifying why this might work. Okay, so if we look at what it can actually do in the context of machine translation, it turns out it's very effective at walking this attention pointer through a sentence as it's doing the translation. So what we're showing here is basically light colored means that this is being, this token is being attended to, essentially. So the encoder hidden states are really now capturing something about the identity of that word in the source in context. And the decoder is no longer having to think about, okay, we have to thread all this information all the way through the network. The decoder now is mostly about picking what states to attend to. So what actually gets learned in attention in seek-to-seek models with attention looks very different than what gets learned in standard seek-to-seek models. They might in some cases perform similarly, or attention only works a little bit better, but the kind of utility here is that we've removed a big burden from the hidden state in terms of what it has to model. All right, and so the last thing I'll say about attention here is about batching. So this is you kind of have to track a lot of stuff here. So when we think about the inputs, the encoder well, when we think about the outputs of the encoder, let's say, we have something that's batch size, so the number of things in our batch, by the sentence length, by the size of the hidden vector. So basically these vectors at the top have some dimension, and so we can arrange these into a 3 tensor. All right, and then when we pass this stuff to our decoder, we have batch size by hidden size outputs from each sequence. And then in our decoder, we have a hidden state that, kind of one hidden state per batch index. And for each of those hidden states, remember we have to compute this dot product or whatever operation you're using with everything from the encoder output. And so this is a little bit, and this is the operation here, and it's a little bit complicated because we end up with attention scores that are going to be batch size by sentence length. And so we have to be very careful about making sure that we broadcast this hidden state in the decoder appropriately to each hidden state in the encoder, and do the right computation, and then do the right kind of reduction over the hidden dimension. And so, finally we end up with these C vectors, and these are also going to be one per batch size, and they have the same hidden dimension as before because we're taking this weighted sum of encoder states. So it's very important when you're implementing this to kind of balance these different, to essentially make sure all of these tensors are the right size, and make sure that at each step you're doing the right operations and kind of reducing or summing out the right stuff, because it's very easy to sum over the wrong dimensions and then things don't match, and then it totally breaks. So that's the kind of advice here about how to batch this up. But the moral of the story is that we've seen how we can actually take this idea of attention and implement it, like build out a fully differentiable process for computing these distributions and these weighted sums, and integrate that into seek-to-seek models. And it really is a very dramatic upgrade for how these models are able to perform. And that's the end of this segment.